Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to work the question sum digits. What this question says is write a function sum digits that takes an integer as the input and returns the sum of that integer's digits as the solution. So given the number 5,510, we do 5 plus 5 plus 1 plus 0, and this yields the solution 11. But this question has one very strict constraint. It says you can't change the input data type. You can only work on it as an integer. So for example, you couldn't say convert this integer to a string, split the digits into separate characters, and then convert them back and sum them. It must stay an integer the whole time. This means that you can only use mathematical operations that are applicable on integers to manipulate the input. So to start, I'm going to do more of a high-level overview. I'm going to kind of walk through what's happening and then really dig down into the logic to show you what to do. So we have our sum digits function, and here we have 6,321, 6 plus 3 plus 2 plus 1 equals 12. We don't really see how yet, but we start with the 6, 3, 2, 1, split them apart and sum them together. But there's no mathematical operations that can immediately do this. There's no built-in functions. We must find a way to algorithmically decompose this number. So now we need to rethink how we're looking at digits. We want to be able to sum them together, and really all numbers can be broken down as sums. In a base 10 numbering system, well, for the number 6,321, it's 6,000 plus 300 plus 20 plus 1. Or looking at place values, it's the thousands place plus the hundreds place plus the tens place plus the ones place. So now we've gotten a little closer to what our sum digits function is doing. We have 6,000 plus 300 plus 20 plus 1, more in line with our 6 plus 3 plus 2 plus 1. So if we take our sum digits and this setup, if we decompose it even further, the thousands place is actually just 6 times 1,000. The hundreds place is just 3 times 100. The tens place is just 2 times 10. And the ones place is just the ones place. It already exists in the form that we need it. So looking at it, we have the numbers we need actually. We have these digits decomposed. We just have to figure out how to get them to this ones place, to get rid of these place multipliers that give them the larger value. And if we decompose it even further, well, we're actually doing the same operation each time. To get to the tens place, we multiply by 10. To get to the hundreds place, we multiply 10 times 10. The thousands place, 10 times 10 times 10, and so on. So if we wanted to invert that, well, if we wanted to get 6 plus 3 plus 2 plus 1, we know that now that's 6,000 divided by 1,000 plus 300 divided by 100 plus 20 divided by 10 plus 1. Or decomposing it, 6,000 divided by 10 divided by 10 divided by 10, and then the rest for the other places. We already saw that our 1 is in the place it needs to be. It's already able to be summed because it's in the ones place. So we can effectively trim this off. We know it is already in the form that we need it, and we'll go over how we actually do this later, but just bear with me in walking through this logic. So 6 plus 3 plus 2 plus 1, we already have the 1 as we need it. So when we subtract the 1, well, we have 6,320, or is 6,000 plus 300 plus 20. And to get this into the next form that we need it, to get that 20 down to a 2 so it can be summed, well, we divide all the numbers by 10, which gives us 632, or 600 plus 30 plus 2. And then now we can add this 2 to the 1, so we trim that off as well. And after removing that, we just have 630, or 600 plus 30. And we can do the same thing to the 30, divide by 10, trim it off, and then it becomes 60, divide by 10, trim it off, and then finally we get 0, and we have moved all of our digits to their ones place and can sum them together. So we have the basic idea, we have the foundational logic, but we don't really have the implementation. We don't have that algorithm we need. So what are we doing? Well, we're converting the items to the ones place and then summing them together. But how do we convert them, and how are we actually trimming off these values? So let's see what happens when we divide by 10 each time. So we have 6,321 divided by 10 is actually 632.1, or as an integer, it's just 632. And we see the same thing for each value until we get down to this last one. 6 divided by 10 is 0.6, or as an integer, it's just 0. So we're dividing by 10 and rounding down, or in some languages, if you have a typed language, it might just convert it to an integer for you. So to get each digit to the one place, we just repeatedly keep dividing by 10 and round down until our overall number reaches 0. Then we know we've worked through all the digits. So now that we're actually converting the items to the ones place, how do we grab that digit in the ones place? How do we say, okay, I know the ones place is this now, and I want to sum it to the other values that I've already put into their ones place digits? And what we'll use is the modulo operator. And what it says is the modulo finds the remainder or signed remainder after division of one number by another. So 5 divided by 2, well, the remainder is going to be 1. 4 divided by 2, that goes in there evenly, so the remainder is 0. 8 divided by 2, the remainder is also 0. And 13 divided by 5, well, that goes to 10, and the remainder is 3. So when we find the modulo of our numbers, well, the modulo 6321 modulo 10 will have 1 as the remainder. 632 modulo 10 is 2, and so on. So this is how we trim off that ones place digit so we know its value to add to the other digits. So now we've really boiled down our logic into something repeatable. We say to find our solution, we repeatedly modulo 10 to get the digit in the ones place, and then we divide by 10 to get the integer representation of this result. We continue to do this until our number reaches 0. The important key words here are repeatedly and do this until. So the other words are the logic, but this is the foundation of the problem, and this is saying recursion. We do it repeatedly and we do it until we reach this case. So this is a great question to understand how to work through recursion. So to really sum this up, to say what our sum digits function is doing, it takes in this integer, and then in the recursive case, it extracts the digits in the ones place using the modulo operator 10. It removes the ones place digit by dividing by 10 and rounding down, or just keeping it as an integer, however your language does it, and then you sum these recursively to the rest of the digits in the number. And we keep doing this until we reach our base case, and that's when our number has reduced to 0. And finally, let's look at the big O of this question. It's actually an interesting case. We're used to things like strings or arrays where there can be an unlimited number of items or characters in that data structure. And integers themselves have a maximum value in most languages. So for example, a base 64 integer will be 2 raised to the 64, which will be this number here, and this is 20 digits. So at most, we only have to process 20 digits, and we're not adding any additional data structures to do so. So this is constant. It's a constant 20 because it's the most that there can be. It's actually a very small number, only 20 items to process. So it's interesting to kind of wrap your head around that and think about it for this problem. And now we're ready to implement the solution. So we said we're going to solve this recursively. For recursion, we always need a base case. So the base case here is going to be when the number is 0. And then for our recursive case, we said there are 3 steps. The first is to get the digit in the ones place. And we use mod 10. The second is to remove the ones place item. And the third is to sum the digits recursively. Okay, so let's handle the base case first. This is pretty easy. It's just if number is 0. In this case, we return 0. We don't add anything to our sum. Okay, so let's get the ones place digit now. And we said it's number mod 10. We also want to get the items in their reduced form divided by 10. So this removes the ones place number and moves the digit after it to the ones place. The one from the tens place will now be the ones place. And we do this by dividing by 10. So we say trimmed items, and we're going to round down. It's just number divided by 10. And finally, we want to recursively get the sum of the remaining items. So we call the function itself sum digits, and here's where our recursion is happening. And we now have this trimmed items, these items that have been shifted by 10. We pass it recursively in. And now we can sum the ones place digit with the sum of the remaining items that we've calculated recursively. Let's run our code. And it passed. So we recursively found the solution by summing the digits by extracting the ones place item each time and shifting the values. This operates in O of 1 constant time and constant space. And with that, we've created a simple but powerful recursive solution. We had this process that we repeated every time, and we transformed our data until we hit our base case. And this is how it's going to work in interviews. You won't be told that, hey, solve this recursively. You need to understand your data and then logic out and evolve into that recursive solution. And this is going to be a great base for the rest of the course and your interviews themselves. You'll be able to handle more complex topics like dynamic programming more simply once you understand how to figure out these recursive solutions. Thanks, and I'll see you in the next lesson.